Unfortunately, today, I'm going to go back to 207. I need some analysis tricks. We had a result where we said, if our function f of t is piecewise continuous, on the interval from 0 to infinity, and f of t is big O of e to the ct for some c, it's of exponential order, and we take the Laplace transform and call that capital F of s, then the limit as s goes to infinity of f of s is 0. A discrete question. What is the converse of this sentence? All that other stuff must be true, right? And we know those don't mean the same thing. I had to put we called it something else. I had to switch it and I had to negate it. The contrapositive. If the limit doesn't go to 0, then none of those things should be false. They can't all be true. So if I wanted a function, say, whose Laplace transform was equal to 1 everywhere, well, then that doesn't go to 0 as s goes off to infinity. And that means either it's not piecewise continuous or it's not of exponential order. So we started to look at functions that didn't obey this theorem, whose Laplace transform wasn't going to go to 0. And we came up with an interesting idea. We're going to call it an impulse function. In particular, I want to call it a unit impulse function. We're going to pick a value between 0 and infinity. I'm going to make my life easy, and I'm going to let A be strictly positive. And I'm going to pick a t0 that's also strictly positive. I'm going to define a function that is only not 0 in a small region around this point. Delta sub A t minus t0 equals 0 or 1 over 2a or then back to 0 again. I would like you to draw me the graph of this function. What's this sucker look like? I need T0 somewhere. There we go. And then I need another number, and I'm going to subtract it from T0, and I'm going to add it to T0. So that's going to form a little bit of a section. T0 minus A, T0 plus A. Now the function is off for all the values down here. It turns on when we get to this dot. Boop. And it goes up to a height of 1 over 2A. And it stays on until where? So that's here. At which point, open circle, it turns off. Now this function is piecewise continuous. Off, on, off, and all those pieces are horizontal lines. They're continuous everywhere except T naught minus A and T naught plus A. So I have a question for you. What's the integral of this function from 0 to infinity? Geometry, no calculus required. It's a box, so it's length times width. Well, height. Height is 1 over 2A. So you just said T naught plus A minus T naught minus A. Simplify that. How wide is this? 2A times, which makes this integral 1. Please notice that works as long as T0 is a number and A is a number. I don't care if A is 13 or 0.0023. It doesn't matter. As long as A is a number, this works. But the graph will change if I pick a different value of A. What if I took the T naught and I left it the same, but I made A half the current size it is? What would happen to the picture if I cut the value of A in half? By comparison to this picture, it would have to get smaller from left to right, right? If I cut A in half. But if I cut A in half that way, the area is still 1. It's got to get taller. Because A doesn't just appear in the horizontal, it appears in the vertical as well, right? So that's going to make it taller and skinnier. If I want the area to be 1 still, it's got to get taller. As a matter of fact, I can think of this idea as a limit. What happens if I think about this as A goes to 0? Well, it's kind of hard to visualize. Take a look on page 329 at figure 752. As I make A smaller and smaller and smaller, the interval from left to right gets narrower and narrower. But in order to keep the area being 1, the height has to get bigger and bigger and bigger. So I have a problem, because really 1 over 2a is going to blow up to infinity. So I should think of this as a new piecewise defined function. And this function should be 0 everywhere except that one spot. And it should be infinity there. This is not a function of exponential order anymore, because it's got a value in it that's not real. Infinity is not a real number. It's an idea. What the fuck are you doing to me? I'm creating what Paul Dirac called a generalized function on the generalized real line. And what he did is he said, you're right. Infinity's not a number. But think about the number line. The number line goes off to infinity. Whether you go off to positive infinity to the right or negative infinity to the left, you're going off to infinity. Ready? If this is the real line, what happens when I do this? I've created a single point at infinity. And all of the same numbers are still there. We can do this. It's called a stereographic projection. And it's easiest to write in complex numbers. If we add a, quote, point at infinity to the real number line, we get this thing called the extended real number line. It's usually written R star, R union, this new symbol, infinity. And the best part about this new symbol is in this universe, it behaves just like a number. The limit as a goes to 0 of delta a t minus t0 is called the Dirac delta function, delta with no sub a. It's also called an impulse function. And not only does it satisfy that upper definition that it only has a value that's not 0 at one spot, and at that one spot, value is infinity, it also satisfies the integral from 0 to infinity of delta t minus t0 dt is 1. By the properties of uniform continuity. Remember that from 207? No, I flushed that out of my brain as soon as I could, man. Why is it called an impulse function? Physics time. What's impulse in physics? And change in momentum comes from the application of an instantaneous force. How long is the ball in contact with the floor while you're dribbling? Teeny tiny bit of time, right? And that change in momentum comes from the force delivered against the floor. If I swing at a baseball, if I make contact, which is already a questionable behavior, I'm only in contact with that baseball for microseconds. But the impulse changes the momentum dramatically. I'm probably never going to hit a 100-mile-an-hour fastball, but it's 100 miles an hour this way, and it's 100 miles an hour that way. That's a hell of a lot of force, isn't it? That's what the graph looks like. Nothing, nothing, nothing. That's the Dirac delta. So it's useful in physics to solve a problem of momentum when my force is applied for just a second, not even a second, a split second. If I take my bouncing spring, right? My lovely spring rig, and I just walk up to the spring and I go, boop, that's an impulse function. What's going to happen? Well, that's exactly what this function does. It tells me, when did you do it? The absolute best part. That's a function defined as a limit of integrals. I can take its Laplace transform. I'm not going to go through the limit definition. If you really want to, it's not that difficult. It's at the bottom of page 329. But it turns out that the Laplace transform is really nice. Remember we had e to the minus as when we shifted? We're shifting by t0, so we get e to the minus t0 s times what? Times 1. because the integral of this function was always 1. This is a function whose Laplace transform is a shifted version of 1. Hot damn. The original Dirac function that is not shifted would only have that impulse at time 0. If I did that time 0 impulse, I'd have e to the 0. Laplace transform would be 1. I found a function that doesn't obey my convergence rule because it's not of exponential order. In a sense, I can think of this as just walking up and poking the system and walking away. And that's what my impulse does as an initial condition in my initial value problems. Now let's picture what actually happens in a situation like this. This is a first order differential equation. If it was homogeneous, I'd just use an integrating factor. And then I'd have to do the integral on the other side. That would suck. So rather than try and have to integrate this Dirac function, I can say, oh, we're going to wait to the count of 2, and then we're going to go, what's going to happen? What would be my integrating factor? If you were going to do this with the integrating factor, ignore this part. What would be your mu of t? I know it was a long time ago, man. Chapter 2. Go back and look at exam 1. That's the coefficient, that's the p of t. So what's the integrating factor? Oh, excuse me. Well, in this case, yeah, t, e to the 3t, right? Except that's a minus, right? Should be e to the minus 3t. And then when I would do that, the left-hand side would become a product, and then I'd end up dividing by the e to the negative 3t. So I should get an e to the 3t here, right? But if I start at 0, aren't I just going to stay at 0 when I solve for the c? Matter of fact, it's this part that tells me when things start. When does this start behaving like e to the 3x or e to the 3t? It shouldn't start until time 2. Let's use the Laplace transform. What is the Laplace transform of y prime? Three cheers for the formula sheet. Then minus 3 Laplace of y equals, okay, here's where I use my new formula, e to the minus s times 2, or e to the minus 2s. What's y of 0? So that's gone. And this gives me s minus 3 times the Laplace transform of y equals e to the minus 2s. So Laplace transform of y equals e to the minus 2s times 1 over s minus 3. I know what to do with that. I want the inverse transform, right? The inverse transform, e to the minus 2s, 1 over s minus 3. What's the 1 over s minus 3 give me? E to the 3t. But what does this do to it? That's this stuff. The extra e to the 2s right here, e to the minus 2s, means I'm going to end up with that Heaviside function. So you're right. Normally, when I see 1 over s minus 3, I go, oh, that's e to the 3t. But because I'm shifting, this is ut minus 2 e to the 3t minus 2. The graph of e to the 3x on a nice, easy window. I know what the graph of e to the 3x looks like. What's e to the 3x look like? And it's pretty steep, right? So if I do e to the 3x minus 2, I pick that graph and I do up and I do what with it? Shift it over by 2 units. E to the 3x, e to the 3x minus 2. On a window that starts at 0. Looks like that. E to the 3x, e to the 3x quantity, e to the 3 quantity x minus 2. It's shifted over 2 units. But I don't want that to turn on until we get to 2. So I'm going to multiply this by something that turns on at time 2. Don't turn on until x is bigger than 2. That is a logical statement, right? Boolean variables, all you programming people. It's either 0 or 1, like it's either true or false, like we did back in discrete. If that condition is not satisfied, that's going to be a 0. When that condition is satisfied, that's going to be a 1. That's the definition of my Heaviside function, isn't it? There's e to the 3x, and here's my new version. and it doesn't turn on. So nothing happens, nothing happens, nothing happens. Then we walk up and go poke, and it starts. Regardless of when we poke it and in what direction we poke it and what times we poke it at, if I can do a little Laplace transform, I can now add this function into the mix. Same settings. This one is going to be more complicated, unfortunately. Okay, hang on a second. Let me think for a minute about the corresponding homogeneous equation. If this was equal to 0, I could solve this right away. What do you get when you set this equal to 0 and solve? Ah, but that quadratic has what kind of roots? What are the roots of that quadratic? I got something different. R squared plus 4R plus 4 equals -9. So I get R plus 2 squared equals -9. So I'm going to get square root of 3i. Square root of 9i, which is 3i. So I get R equals -2 plus or minus 3i. So I should get something with e to the something t cosine of t. and e to the something t sine of t, right? All right, maybe. Let's go back to that. So I know right away, I'm thinking about cosines and sines and exponentials. Matter of fact, let me write down, I would get y equals c1 e to the minus 2t cosine 3t plus c2 e to the minus 2t sine 3t. Let's go back to the original differential equation here. Oh, I need my initial conditions. Y of 0 is 1, and y prime of 0 is 0. Now let's do this with the Laplace transform. What do I get on the right-hand side for my Laplace transforms? Great. Now let's figure out what happens with these first and second derivatives over here on the left. Second derivative. But y naught is 1. Great. Plus 4 times the Laplace of S Laplace of y plus 4 times what? Oh, wait a second. That's not a plus. That's a minus. It's a minus y naught, right? And then plus 13 Ly e to the minus pi s plus e to the minus 3 pi s. All right, hang on a second. The Ly terms, what's multiplied with them? What a familiar looking quadratic. Minus s minus 4 equals e to the minus pi s plus e to the minus 3 pi s. Solve for the Laplace transform of y. S plus 4 get moved over. E to the minus pi s, e to the minus 3 pi s, all over s squared plus 4s plus 13. Well, that's disgusting. Except here's where my thinking in complex numbers comes back to me, because I can think of this as the square complete form, s plus 4 plus e to the minus pi s plus e to the minus 3 pi s over s plus 2 all squared plus 9, which I'll write as 3 squared. Why would I do that in the denominator? It's one of the Laplace transformations on my setup. Well, the top isn't, but that bottom s minus a squared plus b squared shows up in these, which is e to the at cosine t and e to the at sine t, which is what we were going to get if we'd done the homogeneous version. That's why I wanted to think that way. Okay, but now I look back at those Laplace transforms, numbers 10 and 11 from my formula sheet. And I see that for number 10, I need b on top. That's the same number as here. And for number 11, I need s minus a, which is the same thing as in my parentheses. And I got all this other crap up here. So I need to do a little algebra and rearrange this. Fortunately, it's not partial fractions. It's a crap ton easier than that. I'm going to take this s plus 4, and I'm going to write it as s plus 2 over s plus 2 all squared plus 3 squared plus 2 more over the same thing. And then I'm going to write each of the e pieces, e to the minus pi s, 1 over s plus 2 squared plus 3 squared. And then I'm going to write e to the minus 3 pi s, 1 over s plus 2 squared plus 3 squared. This is the Laplace transform of y. Now that actually makes me happy. And not just because I am a sick bastard. It makes me happy because I know the Laplace transform of this thing. I'm sorry, I know the inverse Laplace transform of this thing. The inverse Laplace transform of this first thing is e to the minus 2t cosine 3t. The second thing isn't quite the e to the cosine t sine 3t, because it needs to have a 3 on the top, and I only have a 2. So let's multiply by, I need a 3 on top. That means I need to divide by 3 and pull the 2 out. So I'm going to get a 2/3, and then the e to the minus 2t sine 3t. But wait, there's more. In the same way, each of these has a 1 on top instead of a 3. So instead of a 2/3 at front, I'm going to get a 1/3. So this one right here is going to be 1/3. But there's that e to the minus pi s. What does that do? Yes, but that doesn't help me with the Laplace transform. Not delta, but heavy side. Because it looks like this, right? E to the Laplace, e to the as, e to the pi s, f of s, f of s. This is the Laplace transform for e to the minus 2t sine 3t. It just means I have to shift it over by pi. And I have to multiply by the Heaviside function. All the t's get replaced with t minus pi. Same thing for the next one, only they use a 3 pi instead of just a 1 pi. That, my friends, is gross and disgusting. But let me think about this. This is a second order differential equation. This is a mass on a spring, right? And what happens? It starts out, initial conditions, it starts out pulled down 1 unit at rest and we let it go. So it starts to bounce and then it starts to slow down as it's bouncing. And then we come along pi seconds later and go poke and it starts to bounce again. And then we wait until 3 pi seconds and we go poke again. If I actually graph what's happening on this function, I get a graph, looks like this. There's my spring starting to move and then it slows down. And it slows down until the motion's almost invisible. And then we come along and we poke it. Ready? Poke the damn thing. I think I'm graphing too many things. It's still drawing, as long as it's thinking there. Poke, it starts to move again. And then it slows down again. As a matter of fact, this is a critically damped vibration. We only get 1 period and then we stop. Then we poke it and it comes to a stop. And then, eventually, I promise eventually, we poke it again. Come on, you can draw me the third bump or not? Out here somewhere. We poked it again, and it moved again. There you go. That's the motion of this object. Because this is a very stiff spring. You pull it down, you let it go, and then you come up and poke it, so it goes again, and then you poke it, it goes, that's it. The delta impulse function here acts as a poke. And it literally describes that. I realize now that this is actually a typo down here at the bottom. You see that says at the bottom there, if my function is multiplied by delta t0, that's not shifting property, that's sifting property. S-I-F-T, no H. Because what that does is that pulls out one value, f of t0. Instead of letting the whole function multiply by e of t0, you just get 1 point of your function. So our Dirac delta functional is like a gate that only allows exactly one number through. Example, page 331 on the sifting property. I love Laplace transforms because they do a lot of the crazy calculus part for me, and I only have to do some algebra. But their real utility is just a little weirder than this. What happens if I don't just have one differential equation? How many more do you want? What happens when I start to look at systems of differential equations? Our systems are going to require us to go back and look at our modeling again. So we're going to have to backtrack a couple places in the chapters, and then we'll look at not just Laplace transform methods, but other methods for solving systems of differential equations, which is going to bring back some linear algebra, people. We're going to use that stuff again. I will see you all tomorrow. Tomorrow is question and answer day, 7.4 and 7.5. See you then.